So you go on a fishing trip. You're chilling on the beach, getting your wetsuit on, your spear gun right beside you. You got your paddle board and your paddle, and you're all ready to paddle out past the breakers to try and get yourself some fish. And while you're getting your wetsuit on the beach, you overhear a conversation between two people next to you. And the conversation is about global warming and climate change, and how with ocean acidification, it's going to put activities like fishing at significant risk. And then the other person in the group that you're overhearing this conversation from says, well, they are working on oceanic carbon sequestration technologies. And you stop and you think to yourself, what is that? I've never heard of oceanic carbon sequestration technologies before. I've heard of carbon sequestration and ocean carbon sequestration, but what is that? So let's talk about the science behind that.
Welcome to The Science Behind That with Atticus Hamilton.
Hello, all you scientists. Welcome on back to The Science Behind That podcast. I'm your host, Atticus Hamilton, and on today's episode of The Science Behind That podcast, as you heard from the intro, we're going to be talking about oceanic carbon sequestration. This is a topic that is very near and dear to me, if you will. And it was a topic that was suggested to me by one of you viewers out there. So before we jump in, I'd like to invite all of you to go grab yourselves a nice steaming hot cup of coffee, add a little bit of maple syrup to it, and we'll jump right in. So, oceanic carbon sequestration, what is it? Well, simply put, it is utilizing the ocean's natural ability to absorb carbon dioxide to increase its ability to absorb carbon dioxide as a way of combating climate change. And there's a lot of different methods that are being explored for use, and we'll get into those. We'll talk about each of the primary methods being explored for use, and then we'll also talk about the pros and cons of each, and then we'll summarize at the end of the episode with, I guess, the future directions. So sit back, relax, and if you have any, if you like the episode, if you have any questions or suggestions for the next one, send me an email at thesciencebt@gmail.com, or you can send me a text message using the link below. I'd love to see what you have to say. All right, so let's jump into it. So to start off, the ocean has a great capacity for carbon sequestration. The ocean currently holds 42 times more carbon than the atmosphere does, and since our genesis, it has absorbed 30% of all the CO2 directly released by humans, which is called anthropogenic carbon. So it has absorbed 30% of all the anthropogenic carbon out there, because it has a really, really high sequestration capacity. Between 1,400 and 20,000 gigatons of carbon dioxide is the theoretical maximum amount of carbon that can be sequestered by the oceans. And so because of that, it has been investigated as a potential way of limiting the effects of climate change, because frankly, it seems anymore that nobody cares, and that we just recently passed a milestone of having the most carbon dioxide in the atmosphere at any point in the past 65 million years, if I remember correctly. And that's not a milestone we want to surpass, but we are well on track to surpassing 1.5 degrees C of temperature rise, and probably way above 2 degrees C of temperature rise by 2050. So nobody really cares until it affects everybody anymore, it seems. And so as a result, people are looking into carbon capture technology as a way of mitigating climate change, because in reality, you'll never stop people from using fossil fuels until they've drained all the fossil fuels from the planet. So, what is ocean sequestration then? As I mentioned, it is just leveraging the ocean's ability to absorb carbon dioxide, and it does this through a variety of ways. So, several methods being explored are algae farming, artificial ocean alkalization, electrochemical means, deep ocean injection, and blue carbon restoration. So let's talk about algae farming. So algae farming is actually my favorite because there's minimal ecological or negative ecological impacts for the most part. But it's a very theoretically effective way of at least absorbing some carbon dioxide. So algae, when grown in the ocean and in optimized bioreactors, are about 400 times more effective at removing carbon dioxide than a tree, which is pretty crazy. And there's a variety of different types of algae out there. Diatoms are very effective. They are small, microscopic, silica-based algae. They look really beautiful under the microscope. And they're primary producers. They produce a lot of oxygen. Other ones that are considered are cyanobacteria, and those are found in both freshwater and marine habitats, and they are super effective at removing or at producing oxygen and removing carbon dioxide. In fact, 80% of all oxygen on Earth is produced by the oceans, and out of that 80%, I think it's about 60%, 60 to 70% of all the oxygen produced is produced by cyanobacteria. So they are super efficient at producing oxygen, which makes sense. They were here from the very beginning. They were some of the first life forms on this planet, but they're super efficient at producing oxygen. So again, the ocean produces 80% of the oxygen on planet Earth. So maybe we should be a little less concerned with the Amazon and more concerned with the ocean, considering the Amazon only produces 6% of oxygen on Earth. But anyway, so algae farming is a good way of potentially increasing carbon capture technology because algae is often eaten as food. I'm sure many of you have had those like algae wafers, those seaweed wafers. Those are really good. I like them. But some of these seaweeds and algae that are farmed for the purpose of carbon capture and food production are your giant kelp, your bullhead kelp, your sargasso kelp, and these are all things that people have familiarity with. If you live in California, the big seaweed that washes on the beaches there, giant kelp. If you live in Oregon or Washington, the seaweed that washes on the beaches there, bull kelp. If you live in Florida, the big blooms of seaweed that choke the beaches are called sargasso. And those are effective at removing carbon dioxide as well. They just make the beaches dirty. And so through these methods, theoretically, carbon capture of the ocean can be accelerated just simply by upregulating the amount of producers in the ocean. Artificial ocean alkalization uses the ocean's acid-base chemistry to increase the amount of CO2 that can be absorbed. The biggest problem with CO2, in my opinion, is not the greenhouse effect. Now, this is going to be inflammatory for some of you out there, but the biggest issue with it is not the greenhouse effect, in my opinion. The planet is warming, yes. Currents are shifting, yes, but that is a lot easier for organisms to adapt to than ocean acidification is. And that's as a direct result of carbon dioxide dissolving into seawater. What happens is when carbon dioxide dissolves into seawater, it undergoes an acid-base chemistry reaction and produces what's called carbonic acid. Carbonic acid lowers the pH of the ocean, and pH, as we know, is the number of dissolved hydronium or hydrogen ions in the solution, and a lower pH is more acidic and a higher pH is more basic. And if something has a pH of 2, that's like stomach acid, super corrosive, super acidic. If something has a pH of 12, that's like Drano. It's really good at dissolving proteins and fats, but it doesn't break down metals. It does break down like PVC though. But anyway, regular fresh water is at about a pH of 7 to 7.6. So a freshwater lake is about 7 to 7.6. Compared to the ocean, where the optimal pH is between 8.6 and 9. Now that higher pH is there because you have more unique chemical reactions occurring in the ocean than you do in fresh water. In the ocean, you have a variety of organisms that build shells out of calcium, out of limestone, and out of silica. Corals, they build their skeletons out of limestone. And then a lot of the primary producers like coccolithophores, and then a lot of the secondary consumers like foraminifera produce their skeletons out of calcium. In a more acidic environment, building their skeletons is more difficult. And so as a result, you see a decline in populations of corals, of coccolithophores, of pteropods, which are these little microscopic swimming snails, basically, that form a basis for the food chain. And in a more acidic ocean, it becomes more and more difficult for those organisms to build their shells. And so artificial ocean alkalization would be adding calcium carbonate as a buffer to the ocean to increase its pH, which thereby increases, again, the capacity of CO2 it can absorb. Because there is a point where the ocean can't absorb any more CO2 because it's become too acidic, right? If you mix hydrochloric acid with hydrochloric acid, you're not going to make it any more acidic, right? And in all honesty, if you have vaporized hydrochloric acid over a vat of hydrochloric acid, it's not even going to dissolve in there because it's too acidic as it is. So you can increase the pH of it back to like neutral, which is 7, and then it can absorb more hydrochloric acid. Same thing applies with the ocean. If you increase the pH of ocean water that's at 7.6 back to 8.6, which is a really scary scenario that the ocean would be at 7.6, but if you increase it back to a pH of 8.6, then it can absorb more CO2. So the other big issue with ocean acidification is if we can continue down this route of we don't care how much CO2 is in the air, there will come a point where the oceans don't absorb any more CO2. And then we're really in trouble. But that's how artificial alkalization works. Electrochemical methods, these would be in like vats of seawater. They're not practical to use in the ocean itself, but it involves using electricity and special membranes to separate seawater into acidic or basic solutions, and the basic solutions would absorb more CO2. Then deep ocean injection, this is of course the one that people are gravitating towards because I guess it's the easiest, which is injecting liquid CO2 into the substrate in the deep ocean and or empty oil and gas wells to store it. And this has the biggest risks with it. And we'll talk about those in a minute, but it's exactly as it sounds. Alternative means of mechanical capture are used, for example, filters that suck the carbon dioxide out of the air, or attached filter systems onto gas refineries that absorb all the carbon dioxide produced and sequester it. And then that material is injected into the deep ocean, into the substrate where it's stored, hopefully, for thousands of years. And we'll get into the issues with that. But that would work as well, or that's being explored as well as an alternative. And then blue carbon restoration is probably, next to algae, is the best. Because all this is restoring coastal ecosystems like mangrove forests, salt marshes, and seagrass pads which are highly effective at removing carbon dioxide, and it's just restoring them back to where they were to the pre-industrial area, which helps remove carbon dioxide naturally and benefits the ecosystem instead of harming the ecosystem. So then what are the issues with all these? Algae farming, there aren't really a lot of issues. The only issues that come up with algae farming is when you destroy natural habitat to grow algae, right? So if you chop down a mangrove forest to build an algae farm, that's counterproductive. You don't want to do that. But there are massive stretches of ocean that are, for the most part, barren. And there are a lot of coastal areas that are, for the most part, barren, which can make great substrates for algae farming. And we see this a lot in the South China Sea. China doesn't really have a sense of natural resource management, and so what's happened over the past 100 years is they've basically destroyed the fish populations in the South China Sea. So as a result, you have large patches of area that are relatively devoid of ecological diversity, and so as a result, these farmers have converted these swaths of shallow coastal sea into algae farms. And it's good because A, it sequesters carbon dioxide, B, it provides jobs to a workforce, C, it provides a food source because all that algae that's farmed is then used to eat, and algae grows super quick. I mean, giant kelp grow about 4 feet a day. They grow super quick. And A, B, C, D, E, I lost count, and E, it provides a new habitat again for fish to come in and live. So it also serves to restore the coastal ecosystems, not to necessarily what they were before China or Taiwan or Japan destroyed them from overfishing, but it restores it to some degree by bringing fish species back into the area. So that's a big benefit. Now the issues with artificial ocean alkalization, of course, one of the biggest issues is that's changing ocean chemistry. Anytime you change ocean chemistry, you will have unintended consequences. In my mind, this should be an emergency last-ditch effort thing. In the same sense in the movie Snowpiercer, where they add like a freon-like compound to the atmosphere to cool the planet down. Of course, it went wrong. We should do that is the same thing as this ocean alkalization, where that should be a last-ditch emergency effort because there would be a variety of unintended, unforeseen consequences with that. Electrochemical methods, if they're done on the side with like on the shores of areas, it doesn't really matter, like it's not effective, but it should not be done in the ocean itself because creating layers of very basic seawater with very acidic seawater again will destroy marine habitats. Now the worst one, right? Deep ocean injection. This has the greatest potential for harm because with deep ocean liquid injection, there's too much risk of it leaking out. Because let's talk about this scenario, right? Imagine that you have a company and they take gigatons is too much. They take tons of liquid CO2 and they inject it into an old oil drill site that's defunct in the Gulf of Mexico, right? And I'm not calling it the Gulf of America. In the Gulf of Mexico. They inject it in the Gulf of Mexico. All right, good to go, right? Everything's done. Then it starts leaking. What happens when it starts leaking? Well, there's a lot of data that shows that while certain organisms can thrive in more acidic environments, algae and kelp are one such organism, a lot of organisms would be harmed by that. So if it's leaking directly out of the site where it was injected, it's going to acidify that local area, and it's going to accelerate the acidification of the ocean as a whole, which puts coccolithophore populations at risk. Again, primary producers, not all primary producers, just those. It's going to put pteropod and foraminifera populations at risk, which threatens the food web. And most importantly, it's going to significantly harm coral reefs. Coral are small polyp stony corals, or the corals that we all think of when you say coral reef. Those are super sensitive to a more acidified ocean. And by injecting CO2 into the ocean around it, and then if it leaks out, that significantly puts it at risk and puts the entire reef at risk of being bleached. I mean, 30% of the Great Barrier, or 50% of the Great Barrier Reef is already dead. We don't want to accelerate that process. And so that's just one of many issues or concerns with deep ocean carbon injection. But of course, that is the number one thing that people are, or that companies are investigating as a way to sequester their carbon dioxide. On land, it's a little bit less of an issue, than it is in the ocean. But still, it carries significant risks with it. And then, of course, blue carbon restoration, restoring natural habitats, there's no risks associated with that. That helps everybody out. And it especially helps coastal communities because barrier reef systems are very good at reducing the amount of damage from tropical storms. And as we move into this brave new world, there's going to be more tropical storms. So overall, ladies and gentlemen, I guess my final message for this episode is this. We can't escape being in a warmer future. And that's the simple reality. Global warming is real, and it's happening, and it is going to have profound impacts on our world. Now, the degree to which our planet warms, I think that's still in our hands. You know, if we act, we can maybe reduce it to only 1.5 degrees C of warming, or 2. And if we do nothing, we may go past 2. But the world is going to look very different. And, things like, coastal community restoration or blue carbon restoration, algae farming, those have great potential as methods to remove some carbon dioxide from the atmosphere, and they should be done. They should be investigated. But it can't be the sole means of combating the situation that our species has created. And I guess to leave on a positive note, the positive note here is that nature will always find a way. And I know some people listening to this may have issues with this, but it's true. Nature will find a way. Now, in the future, in a more acidic ocean, will we have the same ecosystems we have now? No. But there will still be ecosystems there. And it'll just change. One example is, most likely, when you have a warming ocean, your coral reefs will fade out, which would be sad, but they'd probably be replaced by kelp forests like what you have off the coast of the Pacific Northwest here in the United States and more of the colder regions around the world. There are a lot of tropical algae species out there, and they would probably be the predominant organisms to take over in a world where the reef systems have collapsed. But again, we don't know what that'll look like, and that'll be left up for time to tell. But there are ways that we can address it, as we discussed. Blue carbon capture technologies and algae farms are a big way that we can address the excess amount of carbon dioxide in the atmosphere and in the oceans. So, ladies and gentlemen, I hope you enjoyed today's episode. I know it was a long one, but it was fun for me to do. I love marine biology and oceanography. I really do. It was my first love, my deepest passion. So I love these episodes. Thank you very much for listening to the Science Behind That podcast. I hope you have a fantastic week. I'll see you all on Friday. And remember, as always, ladies and gentlemen, stand up and question everything.
I drink straight, don't waste time to my place. I feel my heart erase, so catch me if I fall.